Welcome back, everyone. In this video, I'll begin going over the lecture for the work section. Now, the idea of work is very simple, and it's probably something we can all understand. Work measures how much effort it takes to do something. But in physics, there's a technical meaning, and it's directly an application of integration. So that's why we're talking about it in a math class. The work done on an object equals the product of the force on the object times the distance it's moved. So basically what a force does is it allows an object to change its speed. So if you have an object that's not moving, what makes it eventually move an object? It's force. And there's a lot of other ways you can say force is the reason moving objects can stop, and a lot of other things. But specifically, the force F equals the mass of the object times the acceleration the object is moving by. Now we do have to be a little careful just with what we talk about in terms of acceleration. It's not really the acceleration of the object. That's what it is, but it's the acceleration the object is feeling. But the easiest thing to do is just think about it as the acceleration of the object itself, and then the m here is the mass of the object. And if you're familiar with physics at all, you probably are very familiar with the famous equation F equals ma, which is what we just wrote. Now, this isn't a physics class, so you don't need to have a deep understanding of force. Just know that in general, it's the thing that allows an object to change its speed, and its general formula is F equals m times a. That's going to be good enough for us. Now, there are a lot of different types of force, but the main one that we'll be looking at is the force done by gravity. And gravity is an acceleration because you can imagine just jumping up in the air. What is happening? You're not going to be going that speed that you originally lift off with forever. You're slowing down, and eventually you're going to stop at your height or the maximum height that you jump, and then your velocity is going to become negative. So basically, gravity is a type of acceleration, and in that case, we use the formula F equals m times g, where g is specifically the acceleration of gravity. Now, very often when people refer to the weight of an object, it's kind of a little confusing because really mass, m, is supposed to be what a lot of people think of as the weight of an object. Is really the mass. And then the weight of an object is actually mass times gravity. Now, if you're dealing with the regular units, which is what we're pretty much going to deal with, the mass is in kilograms and then gravity is in meters per second squared. We've seen examples of accelerations before, so that should sound a little familiar to you. And then force is in a special unit called newtons. But we don't need to know all of this right now, just when we get to the specific problems. All right, so in general, in this section, since this really isn't a physics class, is most often you will either be given the force itself, so you don't have to figure out m times g, you're already just given F, or you'll be given the mass of some sort and you'll multiply it by g, and you'll be told what g is. And depending on the units, the numbers can change. And then also there's one very special type of force called the force of a spring constant, and that is also going to be one that we'll look at later. But typically you'd be given the formula for that as well. Right. Now, there are a couple of things we can think about here. The force can always be constant. One of the easiest examples is if you think about yourself jumping up, your mass is not changing as you jump up, it's just the mass of your body. And then gravity is always the same. Gravity is always felt the same, unless if you go really, really, really far away from Earth. But we're only going to be jumping a couple of feet at most into the air, so that's not going to change. And if you multiply your mass times the gravity, acceleration of gravity, you get your force, basically your weight. Well, that's an example of a constant force, so it's not changing throughout the duration. And when you do not change the force, the work is very, very easy to calculate. So if force applied to an object is constant, then you can find the work done on the object by W equals F times D, where F is the force and D is the distance traveled by the object. Right, so if you jump up in the air 2 feet and then back down 2 feet, the D would be 4 because you went 4 feet. And then the force based on your mass and the gravity and the units you're in, you would just multiply the two numbers. But just to see it in action, we'll look at a problem here. So it asks how much work is done when a mom gorilla carries her 50 kilograms son up a tree for 25 meters. And this is what I was talking about before, is that you may not be very familiar with the force due to gravity, but if you're in meters per second squared, then gravity is numerically 9.8. And these are the normal physics units. So if you're curious about why it's meters and seconds, that's because it's the normal thing to use. Right? Well, work, why is this just F times D? Why is the force not changing? Well, the force isn't changing because we're given the mass of the mom, or sorry, not the mom, we're given the mass of the son, 50 kilogram son. So M equals 50. We'll go ahead and write kilograms since that's the units. And what's happening here, what is the force? Well, one thing to realize is that we need the force and the distance to figure out the work. Well, the force equals M times G. And you can understand why this would be due to gravity, outside of the fact that they are telling us we should probably be using gravity for acceleration. But if you're climbing a tree, then you've got a tree right here, and you're just going straight up. So what are you fighting against? You're fighting against gravity. So the force is gravity. And when in doubt, especially if you're moving vertically, you're going to be thinking about force as mass times gravity. All right, so that's all we've got. Now we can go ahead and compute this. The mass is 50 grams. It's never changing. Sorry, 50 kilograms. And then gravity G is 9.8 meters per second squared, which is also never changing. Now, if we go ahead and multiply these numbers, you get 490. 50 times 9.8 is 490. And the units kilogram times meters per second squared actually has a special name called a Newton, named after Isaac Newton. Now, if you're not familiar with that, you can think of it as just the letter N, but one of these is called a Newton. And it's just named after Isaac Newton. He pretty much discovered a whole bunch of things about physics and gravity and acceleration and forces and everything like that. Now, if you use different units to represent the mass, so 50 pounds, maybe American units, 50 pounds, and then you probably use different units for gravity as well. It wouldn't be 9.8, it'll be another number with different units here. You'll have a different kind of unit for force. But for force, we like to just use the standard one, so we're just going to use newtons, unless otherwise told. And the nice thing is that this is your F, 490 numerically, and that's what we need to plug in. Well, what is the distance? That's just the distance traveled, which is 25 meters. So D equals 25 meters. And we can go ahead and plug that in as well. And because the force is not changing, this is just a multiplication problem. Work is 490 newtons. I'm just going to include the units here to explain the end answer as well. And then the distance D is 25 meters. Well, what is 490 times 25? Kind of a big one, so let's go ahead and just grab the calculator. 490, times 25 is 12,250. So numerically, our work is 12,250. Now the unit here is newtons times meters, because we just have newtons times meters. But this is also given a special name because work is actually a type of energy. You don't have to know all of these things. I'm just explaining why it has a special one. So force has a special unit because this is kind of messy, but newtons times meters is given the unit J for joules. So that is a J, and it stands for joules. So if you see J anywhere, capital J after a number when you're computing work, it stands for joules. And 1 joule is 1 newton times meters, and a newton is this. But once again, if you don't really aren't concerned about the physics part, That's understandable. We're just really concerned about how you do these work problems. The newtons, the joules, all that stuff, it'll come to you if you take a physics class. All right, so the main issue is that what happens if our force is not changing? Because if if our force is changing, because if it's not changing, this is what's going to happen every time. You're going to either be given the force or figure it out, probably based on gravity, like this, m times g, and then multiply it by the distance. So ultimately, it's not going to be a challenging problem if you don't have a changing force. But if your force is changing, then what's going to happen is, no surprise at this point, we're going to have to set up an integral to solve the work. And really, there's two kind of main examples that are relatively easy to explain. An example of something natural is when you stretch a spring farther than its equilibrium point. So if you have, like, let's say a spring attached with some sort of mass at the end and just sits here. Just imagine you're holding this, but when you let go, it doesn't move. Well, if you grab it and you push it out, grab it out this way, so you're standing over here and you grab the mass and you yank it out this way, what's going to happen is it's going to shove itself back in. That means the force is changing because as you let go from one position when it was in equilibrium, it didn't move, but in another position, it did move, which means you applied some force to it because you made it change position. You made it move. Right? Basically, you changed something. Right? So that's one example. Another example is when you go underwater, the deeper the depth, the more you feel from the water on top. Basically, there's more weight of water on top of you. If you're 1 foot underwater, you might not feel much. If you're 100 feet underwater, you might be kind of hard to breathe. So that is another example, is you're feeling more force. It's more and more as you get lower and lower. And then there's also a lot of examples based on this sort of idea with depth. So if you have like something hanging off the side of a building, so you have some building, it's however many feet tall, and something's hanging off of it and you want to pull it up, maybe like a really, really heavy rope. The longer it is hanging off the building, the more weight there is because there's just more rope. And as you pull it up, you'll probably get tired, but it's, in theory, if you did not get tired, it would be easier and easier as you go because you'd have less and less rope to pull up. Everything that you pull up would just be sitting there on the side of the building, wherever you're pulling it up. So because the weight's changing, which is like the force is changing, right? And in most examples, changing force is what's happening. You're not going to have a lot of examples with constant force. Now, just to quickly derive the formula, well, if we pretend that f of x is the force acting on an object that moves along the x-axis in the positive direction from x equals a to x equals b. So what I'm saying here is, let's say we have a box of some weight, pretend it's on the x-axis. I just have it floating up here so you can see the difference, and it's not just sitting on top. It starts at x equals a, and it ends up at x equals b. Well, how much work did you do? Well, as you travel through, as you go through, maybe you start off pushing it really softly. Maybe you're moving the box yourself. And then you get more and more energy as the momentum starts to build and it starts to move faster. But then after halfway, it starts to slow down again because you're getting tired. That means the force is changing because you're pushing harder and then lighter. Well, the idea is and we're not surprised, we wouldn't be surprised by this, is we break it up into many different intervals and we just multiply the work done at each part. So the work done may be from the first little section here. I'll highlight this real quickly. So maybe the work done here, well, this is F times D. Whatever D is doesn't matter. It's at this point, because we don't really have a label for it, just like some change, D. And then the force, maybe you take the average force you push with at the first little section. Well, that's going to give you some work. And then maybe at the next step, maybe these are each 1 meters and you're pushing it 100 meters. Then maybe the next step, you push it a lot harder. So you apply a lot more force, and that means my rectangle, my visual, the amount of work I'm doing is increasing, but it's changing. Well, We've seen these a lot where you just add up all the areas of these rectangles. It's just that this time the height of the rectangle is the force and the width of the rectangle is d. Well, that's exactly what we're used to. If we write it out before we write our integral, which is just the formula below, we would have the sum of f, oops, let me use capital F because that's what I've been using for force, capital F of x sub I, where each of these is like an x sub I, and then it's times, I'm going to label it as delta x, the change in x, instead of just calling it d. So if we only did one full movement here, we only had to move it once, like one push, whatever you want to think about, and we got it from A to B, then our delta x would be the whole thing. But if we have a lot of little pushes that we want to add up together, we have this. And the idea with the Riemann sum is always to get an exact answer here. So we do the limit as n goes to infinity of the sum of I equals 1 to n of this. And then the delta x is just your typical b minus a over n. And this is our Riemann sum. So that exactly tells us to get the work done on this object, all we do is we integrate the force function, capital F of x, from a to b. Now, just like with the previous sections, before we start doing problems, I just want to remind you that the fact that we're using x is not important. If you move something up and down and it helps you to use the letter y instead of x, just use the letter y. But the whole point is that in order to compute the work, we need to integrate the force function from x equals a to x equals b. And just like with the other application problems, we haven't talked about any new integral formulas in quite a while. We're just using the same ones over and over again. So the main challenge will be setting up the integral. Right. Now this is a good place to stop. And in the next video, we'll actually look at a couple problems dealing with varying force. So I'll see you there.